Section 11.4 is really interesting. And I'm going to combine what is really a little bit of calculus with some geometry and some algebra and some really careful observation on your part on how numbers change. So we have gone through and found the areas of various objects, like I went over the last video. Squares, rectangles, parallelograms, trapezoids, triangles, and really in regular polygons. Now, the sequence of that is important if you're writing this text or if you're developing any sort of geometry here, because what we want to do next is try to figure out circumference and area of a circle. And here's the logic on this. And if you're looking at page 446, the argument that they develop here is really, really good, and you should look it over carefully. Basically, the idea is that as we keep adding sides to regular polygons, we come closer and closer and closer to approximating the sides of a circle. So the more sides that we have, the closer the area of the regular polygon becomes the area of a circle. So that is all over here in this chart that I've brought over from page 446. So look carefully at this. This says we're going to increase the number of sides of a polygon. And using r as the radius, the standard radius for this particular drawing with all of these polygons inscribed into this circle. If we calculate the perimeter for each one of these sides and the area, now these are all using the area calculation for a regular polygon and using r as the radius. Here is what I want to point out, that as we get greater and greater number of sides here, we go from 4 to 100, you notice that the gaps in between the perimeter become smaller and smaller, and the number becomes closer and closer. And it gets to the point where in math we call that a limit, or a limiting element, or a limiting factor. Similarly, as we calculate area, we notice something very similar, that the gaps in between become smaller and smaller, and we get to a point where, once again, we see that this becomes somewhat of a limiting factor. And essentially what we, in a very roundabout way, is proving the existence of a very important concept in math, and that is the notion of pi. And pi is defined as not 3.14 and how many decimal points. It's an irrational number. It does not repeat. It is like the square root of 2, as I have always talked about, is the square root of 2. It is irrational, meaning that its decimal doesn't repeat at any point. Pi is the same concept, and pi is equal to the circumference of a circle divided by its diameter. And that is the one thing you'll always need to remember. Pi isn't 3.14 whatever. Pi is the circumference of a circle divided by the diameter, or the circumference of a circle is equal to pi d. Very simple. That means that if d is equal to twice the radius, then the circumference of a circle is 2 pi r. The circumference of a circle is equal to pi d, and if we look carefully and look at this number over here, 3.14, when this number of sides increases infinitely, we approach this number, which approaches the value of pi times the radius squared. So we end up with the formula for the area of a circle is pi r squared. So this is really a very nice piece of mathematical logic here that is on the page. Now, doing the math of this is much easier. It's pretty formulaic. You drop in the numbers, very recipe-like, and calculate various aspects. What I do want to stress with you guys, as it says on my test sheet, unless I ask you otherwise, pi remains as pi, always. I never want you, unless I tell you to actually substitute, always just use pi as pi.